So welcome everyone, and thank you for joining us today. This is now episode 5 out of 6 for this series of webinars on how electron diffraction is transforming research across materials science, life sciences, and chemistry. My name is Fraser White, and I'll be your host today. It's my pleasure to introduce today's presenter, Joshua Bocarsley. Joshua is an assistant professor at the University of Houston and has been working on battery materials since his postdoc at Cambridge University in the UK. He's recently begun using electron diffraction in his research, and today he's going to share some insights into just how this technique is applicable to battery research. Before we get to the main presentation, I just wanted to inform you of a few quick items. So as always, if you'd like to ask a question, please do so using the Q&A button, and these will be read out and answered as time allows. Any unanswered questions will be responded to after the session. Where applicable, if you can, please try to include the slide number so that if we're answering the question at some point later on, we'll be able to understand the context more easily. The chat is open, but please note that if you ask questions there, they might get lost as I will be posting links into the chat as we go along. We will be recording this webinar. The recording will be available from tomorrow. If you have any trouble watching the presentation live, we recommend that you catch up via the recording, as it's unlikely that we'll be able to resolve technical problems during this live webinar. So as I said before, this is the 5th episode in this series. The preceding 4 episodes are all available via our website. You can also register for the final episode, which I'll post a link for just now. And that will be on the 6th of August. So if you're interested in MOF research with electron diffraction, then please do register for that one. It should be very interesting. Okay, so thank you for your patience. I'll now pass over to Josh. So Josh, whenever you're ready.
Thank you very much, Fraser. And thank you for that introduction. As was said, I'm an assistant professor at the University of Houston, and my group is really interested in the structure of battery materials. We think that the structure of a lot of the different components of a battery are critically important to the performance and to designing better batteries. A lot of my background was in solving these structures using very high resolution powder diffraction techniques and structure solution from powder diffraction. And we've now moved into electron diffraction as a way of getting more information out of these small crystals. Here's a quick outline of the webinar today. I'll start with a background of some of the basics about lithium and sodium batteries, highlight the importance of structure and crystal structure in this field. We'll talk about micro-ED or 3D electron diffraction as a tool for batteries, and then go through 2 sort of real examples of batteries with different sample prep, data collection, and structure solution. All right, so without further ado, let's get started with the basics. Most of us here should be familiar with batteries. Probably you're listening and watching on a device that has a rechargeable battery in it, perhaps multiple, and really around you in the room you're in, there's potentially half a dozen different batteries of different types. So these have really revolutionized personal electronics in our modern world. They're everywhere. A basic picture of what one would look like. Let me grab my laser pointer. One of the most basic batteries would be a metal battery as shown on the left. And that consists of 2 electrodes, a positive electrode, which is shown on the left. In this case, it's a metal oxide, like lithium cobalt oxide, LiCOO2, with a layered structure, typically. So the cobalt oxide layers are shown here, and then in between there's lithium or a different alkali metal. And that structure is really helpful because it allows the lithium or sodium to move back and forth and to be extracted with very high mobility. And then there'll be a negative electrode, and that could be graphite or silicon or just the bare metal. In this case, I've shown it as the bare metal, lithium or sodium. And we've set these 2 electrodes up in a clever way so that in between them, there's a separator that's ionically conductive, a salt solution typically, but electrically insulating. So you can get ions across from one electrode to the other, but if the corresponding electrons want to go, they have to go through an external circuit. And we can use that to do some work or to charge the battery. So if we apply, in this case, electrical current Through this wire, we can force electrons from the positive electrode to the negative electrode and charge up the battery. The corresponding ions will go to meet the negative charge. When it's time to discharge the battery or use it for some task, the reverse process will happen, where ions will flow from the right to the left and electrons will go to meet them, and we can use those electrons for work. So in doing that, we need materials that can accommodate a variable amount of ions. So typically these lithium metal oxide that are used in modern batteries, when they're totally discharged, they have a formula like LiMO2, where M is metal or mixture of metals. And then when charged, you can get about half of that lithium out, or sometimes a little bit more, depending on your chemistry. And you can, what's nice about these materials is that you can do this process very reversibly, where you can go back and forth between charged and discharged states, potentially thousands of times without too much degradation. Okay, so that was a cartoon of how batteries work. Of course, in a real system, things could be a little bit more complex. We have interfaces of various types. So here's a nice figure showing a few different types of batteries that are used, metal batteries that are used. What you can see is that in a real battery, you're going to have some finite particles, shapes to your cathode or positive electrode. And then depending on your electrolyte, which could be either a liquid saltwater solution or a solid state ionically conducting electrolyte, you'll have interfaces between the positive electrode and the electrolyte, between the liquid electrolyte and the anode, which could be lithium or graphite. You have all sorts of microstructure that can form on the metal site, as well as interfaces, side products. This is called a SEI, which is a small interface of organic and inorganic components all mixed together. So there's a lot of structural elements that are all working together to make this battery work. As you charge it, you can also imagine that the cathode is going to lose some of the lithium is going to come out, and that is going to cause it to shrink in size or grow in size, depending on the chemistry. There could be stresses, strains, cracks, additional side products, gas evolution. And so understanding all of these processes is really the key to understanding how batteries work and how to make a better battery. Mm-hmm. And for personal electronics, the batteries that we have work quite well. Probably your phone lasts for a while, at least. And perhaps we'd like it to last a little longer, but I think they've really come a very long way in the last decade or so. But the reason that we're still interested in battery research is the next frontiers of battery deployment are really large. So for example, here's an electric vehicle. And I like this figure of an electric vehicle because you can see where the batteries are. The yellow here is the batteries. And a typical electric vehicle has 450 kilograms plus, even up to a ton of batteries in it. And in this case, it takes up the entire undercarriage of this vehicle, and it can be the majority of the weight of a vehicle. So suddenly, when we talk about deploying a lot of electric vehicles around the world, we're talking about a large mass of batteries and a huge amount of resource use. For reference, the capacity of a typical electric vehicle is around 50 to 100 kilowatt hours of battery capacity. So keep that kind of 10 to the 2 kilowatt hours in mind. And as big as the deployment in electric vehicles is, the next frontier is going to be significantly larger, and that's grid scale energy storage. So in this picture, you can see in a South Australia wind installation, and you see you have a windmill here, and what's next to it, a massive battery bank. This was put in around 2020, and it's a 200 megawatt hour. So we've now gone up 3 orders of magnitudes compared to a car battery. And the reason is that when it's windy, the wind farm produces a lot of energy and everyone can use that energy. But if you want to have a renewable energy system and you want power when it's not windy, when it's not sunny, you'll need some way to balance the load. And batteries are one of the best ways to do this. Really, really massive batteries that can be charged when it's windy and then can provide power into the grid when it's not windy. Okay, so this is around 200 megawatt hours and costs about 110 million USD using conventional lithium ion battery technology. Here's a plot of the cumulative US utility scale battery power capacity in the USA. And some of this is projected into 2025, around 26 gigawatts. In this case, this is in gigawatts rather than gigawatt hours. And you can see we're sort of at the beginning of what looks like an exponential rise. Fully renewable economies would require hundreds to thousands of gigawatt hour of grid scale battery capacity per country. And so you're really starting to see deployment on absolutely massive scales. We're many orders of magnitude larger than personal electronics. Okay, so you could probably guess what the problem with that is. And the problem is that our state-of-the-art lithium-ion batteries perform really well on small scales. They charge pretty fast, last long, maybe not as long as we'd like to, but have high capacity. But they tend to be quite expensive. So cobalt, nickel, lithium, and copper are all involved in the standard battery chemistries that we use. They're all varying degrees of rare and expensive elements. Lithium, just to start with, had a peak spike in price around 2022, partly because of all of this battery demand that's growing. Lithium carbonate is only made in a few sites around the world, and the trade is quite complicated. We call this a critical element. And so for a next generation of batteries, we are looking for batteries that are high energy density, safe, long lifetime, and also cheap. And of those four, you can guess which one I think is the most important. Probably cheap. And one way we can start to think about cheaper batteries is to go one row down on the periodic table from lithium to sodium. And sodium, unlike lithium, chemically very similar, but is very abundant all over the world. Every country in the world has access to it. And if we look at the price of sodium carbonate, it's not even visible on this axis. It's basically just sitting down on the x-axis. Nearly free compared to lithium carbonate, with massive supply chains already set up and available to every country on the world. This is, essentially salt. Okay. All right. So why haven't we used sodium already? One of the reasons is shown in what's called a Ragone plot over here. And what this shows is on the x-axis, the gravimetric energy density, so the watt hours per kilogram of your battery, and on the y-axis, the power density. That's how fast you can charge or discharge the battery. And the ideal battery material or battery chemistry would be up at the top right with a very high energy density and also power density. The lithium-ion batteries that we currently use are all in this sort of region, mostly either NMCs, nickel, manganese, cobalt, chemistries, or lithium iron phosphates, LFP. And sodium sits just a little bit lower in both the power and energy density axes, and that's because sodium is larger. It simply weighs more. There's a slightly different voltage potential associated with it, and it's harder to move through your material, so it moves more slowly because it's heavier. As a result of that, sodium-ion batteries, the chemistry is a little bit harder to work with, and they'll be a little bit less high performance than some lithium-ion batteries. But as you can see, you can push sodium up into the regime where it's competitive with lithium, especially for its price. And critically, you can do this at much lower cost. So as we're talking about deploying batteries on the absolutely massive scales that are needed for a renewable energy economy, sodium is sort of the next frontier, I would say, and has just started to enter the market in a large way in this year. There's also some next generation technologies that are a little less mature, lithium metal, lithium sulfur conversion batteries, and various others that will potentially push us even farther in performance. But those are a little bit farther out. All right. So I think that takes us to our first question.
Yep. So I've just launched the poll. We would like to know which field you're working in. If you're an academic working in batteries, in industry working in batteries, you're a crystallographer, or you are other, whatever other may be. So it looks like the majority of the audience are crystallographers and some academics working in battery. Okay. So I'll let it run till about 2/3 of the audience, although everyone seems to be interested in participating, but nothing is really changing with the breakdown. So I will stop it there and we can move on. Thank you, everyone. Okay, when you're ready, Josh.
All right. Okay, so let's dig in a little bit to how batteries work, how we get energy stored. Going back to our cartoon picture with our positive and negative electrodes, cathode and anode as they're typically called. As you charge the battery and you drive a current from left to right in this cell, the voltage that you measure will increase, and that's shown in a plot that looks like this on the right. So the x-axis of this plot is the specific capacity in milliamp hours per gram of your battery, and the y-axis is voltage. Now, note that the current flowing is also corresponding directly, one electron to one lithium ion moving through the battery. So we can correlate that specific capacity directly into a composition of our cathode. When we start out, before we've charged, we have a composition, in this case, of lithium 1. It says 1 minus X, where X is 0. Nickel 0.8, manganese 0.1, cobalt 0.1, O2. So our transition metals are what's called NMC cathode in this case, nickel, manganese, cobalt, all mixed together. And we're going to start fully lithiated. And then as we charge the battery, we are going to pass current across the cell, and we are going to deintercalate lithium. And so our X is going to go up from 0. And with this material, you can actually get 85 or even 90% of the lithium out. And your voltage will continuously go up, 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 up as you do that, till you have an almost delithiated cathode. Then you can use this battery and discharge it, use it for some task, and then the voltage will go down, following ideally, a very similar curve with low hysteresis. That's a sign of an efficient battery. And then often what you'll see is that as you go to discharge the battery, you don't get the exact same capacity out. There's some lost capacity. That's an inefficiency in the first cycle. You can't get all of the lithium back in. But the voltage, as we go through these cycles, is going to go and increase as we're charging the battery and decrease as we're discharging. And it oftentimes isn't perfectly smooth. There's some shape to it. And you can imagine that the exact shape of the battery is going to, of the cycling curve, is going to depend on the chemistry involved, the energetics of the various phases involved. And optimizing this cycling performance is a big challenge. If you look at these cycling plots a fair amount, this is a charge-only part, and this case, actually, the x-axis has switched around. So now we're going from right to left as we charge. You will often see different types of charging profiles. And so looking at this NMC, the nickel, manganese, cobalt again, there's some features as it charges, but it's relatively smooth. And that is a signature thermodynamically of what's called solid solution type charging, which means that the cathode goes through a solid solution with random lithium on the lithium site as it charges, where you just remove randomly lithium and you stay basically in the same phase. There may be some changes in lattice parameter. There probably will be. There'll be strains, but there's no obvious phase transitions in a plot like this. On the other hand, a lot of times when you make a sodium ion cell set up the exact same way, you get a much more step-like profile. So here is sodium cobalt oxide. And as you can see, as you charge, it doesn't smoothly go up, it goes through steps. And that's the thermodynamic signature that this is going through multiple phase transitions. Each of these steps is a single phase, and then the plateaus between the steps are a two-phase reaction, where sodium, because it's larger, it doesn't smoothly come out, but it has a larger effect on the cathode as you try to remove it. So as you try to remove this larger sodium, it will jump at stable phases to another stable phase and go through lots of phase transitions. For your battery, if you try to do this thousands of times, charging and discharging your battery, this can be a major cause of degradation because you're going through phase transitions that could have small amounts of hysteresis. There could be cracking as there's volume changes, built up strains, dead areas, etc. Yeah. So it's really common when we're looking at sodium cells, because of the larger size of sodium, to get this steppy phase behavior. Okay. If you were to just analyze the shape, you can draw single phase and biphasic regions on the basis of all the steps as well. And you can see it's a lot of phase transitions. There's a lot of phase transitions. And hopefully, since we have a lot of crystallographers and battery researchers here, the question you should be asking is, what are those phase transitions? They can be quite complicated and quite interesting in sodium materials. There's all sorts of different subtle phase transitions that can happen that are critically important to the behavior, but can be quite subtle. So for example, if you have these layered structures, the layers can slightly shift relative to each other. Those are called stacking sequence transitions that change the coordination of the sodium from prismatic to octahedral or vice versa. Then also the sodiums, as you start to take some out, they can form stable patterns. These are called sodium-vacancy orders. So here's an example. Rather than the sodium just be partially occupied across the sodium site, it forms a superstructure where it's patterned into some interesting pattern. And how it patterns is going to dictate how the sodium can move and whether it can move effectively, and therefore whether the battery is able to be charged and discharged well. And then you can also get effects in like transition metal layer as well. Ordering can happen depending on the sample prep. And also you can get migration of transition metals. Okay. So as an example with the sodium cobalt oxide, a lot of the structures are not available. You couldn't download a CIF of most of these structures, but there's computational work, some nice computational work, for example, predicting that a lot of these phase transitions are associated with jumping from one stable sodium vacancy ordering to another. So like this one at 5/11ths, this one at 1/2, this one at 4/7ths, and so on and so forth. You can imagine knowing each of these structures would really be the key to knowing how this battery cycles and how to ameliorate any negative impacts of the phase transitions. But if you were to look into, for example, the ICSD, you would find it's very hard to find an actual downloadable CIF verified structure of most of the phase transitions, even in a relatively simple material like a monometallic layered transition metal. And the reason for that we've looked at in our lab quite a bit, and that is that even though these phase transitions and these sodium vacancy orderings are absolutely determine everything about the battery voltage capacity and reversibility, they're quite subtle to study experimentally. So here's a powder diffraction pattern, and we're trying to simulate it with a model of sodium vacancy ordered superstructure. And what you can see is, this is lab-based copper K alpha powder XRD. What you can see is the main peaks from the framework are shown and fit the data quite well. But we have to zoom in to the noise, essentially, of our XRD to see where the superstructure peaks arising from that sodium vacancy order would be. And in this scan with the lab XRD that we were using, the peaks that we expect to see are hidden in the noise. There's really no information we can get about that superstructure ordering from this scan alone. So again, critically important, but very subtle to see with diffraction. So one approach, and one of the most promising approaches, is to go and get synchrotron X-ray diffraction, as well as other high-resolution structural characterization techniques. This is some really nice work from James Steele, who is a PhD student at Cambridge, who I worked with when I was a postdoc there. And what he did is he took sodium nickel oxide and he desodiated it to a specific state, Na2/3 NiO2. And he took that sample to I11 synchrotron and did some really high resolution synchrotron diffraction. And in doing that, he was able to see the superstructure peaks more clearly in the data. And he was able to very carefully model this with Rietveld refinement and come up with a model that fits absolutely beautifully. He also wanted to make sure that he was able to accurately reproduce the oxygens. And so he went and did high resolution neutron diffraction at ISIS neutron source. And so he was also able to see superstructure peaks even in neutrons. You can imagine with neutrons, this is a very challenging experiment. You need to find a way to make a large battery that has a large massive sample in it, carefully charge it to the right state, and measure very carefully to see such tiny features. Fitting is also quite challenging because you should be very careful to come up with a reasonable structural model on the basis of tiny superstructure peaks. But the structural model it came up with shows the sodium zigzag ordering quite nicely, and also finds out from the ADPs and different forms of modeling that it's a very dynamic structure, and that a lot of how the battery performs is probably related to how dynamic the vibrations are as the battery starts to be charged, which is quite interesting. Okay, so that's very beautiful work, but as you can see, it's very labor intensive. You need access to national facilities and quite challenging. Okay. Since we are quite a few crystallographers in this audience, the obvious question is, how can we do this with single crystal? Because single crystal would be a wonderful way to look at superstructure orderings. It would be sort of the ideal technique to pick out these weak reflections and solve them with a lot of certainty. The problem is when you're working in real batteries, we don't have single crystals. Typical battery materials, they range in morphology, but here's some SEM images showing the kind of spectrum of what you could expect. On the left is what we call a polycrystalline battery material. And that term, polycrystalline, in the battery world means that there's individual particles, and each particle is made up of a lot of small crystallites with different orientations. And then with different temperature treatment, this group was able to make what is called single crystal NMC battery materials. That term single crystal in the battery world means something very different than single crystal in crystallography. What it means is you have a powder, but each individual powder is a single crystal, essentially. And so you can see the difference in the SEM image. So even in these single crystal materials, the particles have to be quite small because you need to be able to make this into a battery where lithium or sodium has good transport across the surface area. So this is about 1 to 2 microns is typical for the single crystal size that you can expect, even in your most crystalline battery materials. When we're a little less careful working with new materials in the lab, our samples typically look like this. They're a little less controlled, so they'll have a range of shape and size, often flat platelets because these are layered structures. But they're very far from single crystals that we could use for single crystal data collection in a lab XRD. All right, so that will set up the problem. I'm going to pause now for questions about the background and the issue before we go to how we're trying to solve this with microED.
We've got a couple of questions in already, so if you still want to ask a question, please do while we're covering these ones. So the first question, you mentioned that sodium batteries have issues not present with the lithium technology, and it seems that this might be a key reason that lithium batteries took over despite both being about a similar age. At this point, it seems that sodium is not as well researched and has bigger problems to overcome. So after researching for several years, do you think sodium can reach the same level as lithium? And if so, how long do you think it will take for sodium to become a mainstream commercial choice?
Yeah, that's a great question and very astute. The reason we use lithium is absolutely if you make these batteries, especially with lithium cobalt oxide and the standard electrolytes, they just work very nicely. Lithium is small, moves well. Sodium is a little harder to work with, a little harder to get to work well. And I think that scales up to industrial levels. And that's the reason why lithium has been the technology that took off first. In the last 2 or 3 years, CATL in particular and a few other companies have commercialized the first sodium cells. The first sodium cells are actually available. You can get your hands on them. Modern sodium-ion battery cells are available now in 2025. You can get your hands on them. So I think they are now reaching the level of maturity where essentially they're going to start to take over. They're not going to take over from lithium entirely, but they'll be complementary when you need a lower cost, better environmental impact. I think essentially it's starting this year. Yeah, great question.
Okay, so another one, I've heard of other battery chemistries pitched as an alternative to lithium ion over the years, such as aluminium ion batteries. Claims are often higher storage density, more charge discharge cycles, and so on. Have you investigated any alternatives, or do you have any comments or opinions about them?
Yeah, sure. So there's quite a few. There's a pipeline between new lithium technologies, lithium sulfur, lithium air, multivalent ions, aluminum and magnesium, which carry more charge and can store more. All of these, I would say, are much, much less mature than lithium, certainly lithium ion, and much less mature than sodium. So there's a pipeline. The way I think about it is there's a pipeline of the next new battery technology currently being introduced that's about to be introduced on larger scales is sodium ion. There's technologies that will take about 5 years, 10 years, and 15 years. The level of maturity between a lot of those technologies is very, very low compared to sodium ion. One of the biggest advantages when you think of practically what the next technologies to be developed are is that sodium ion is similar enough to lithium ion that you can use it as a drop-in replacement on a current. So anything that involves building entirely new infrastructure is going to take longer. Sodium, some of the sodium cells that have been made, you just take a lithium battery manufacturing plant, and 1 day a week you make sodium cells. It's similar enough that you don't have to rebuild the infrastructure.
Okay, we have another couple. How do you confirm single crystallinity and polycrystallinity from SEM?
So from those SEMs, you can see sometimes grain boundaries. If you want to really confirm, you would probably need to pull out individual crystals. Oftentimes we have pulled out individual crystals from those and found out that they're really multi-crystals. So that's a good question. I would say you can't easily, but certainly you can see the difference between the single crystal style materials and the polycrystalline. But it doesn't mean, strictly speaking, that they're all perfect single crystals.
Okay, I'll do one more before we move on because I'm interested. Any way we can prevent batteries going on fire?
So batteries going out on fire, absolutely a big issue. And safety, lithium-ion batteries, the main component that is dangerous there is the organic electrolyte, actually. So the organic electrolyte is what catches on fire first, frequently. If you have a lithium, you don't typically have lithium metal in your cells, but you can have small dendrites of lithium that form, short the cells, and catch on fire. So a lot of the work to make safer batteries is actually focused on the electrolyte. Can we replace that electrolyte, that's some organic solvent that can easily catch fire, with a solid material that doesn't easily catch fire, then we can have safer batteries. So this is a big reason why people are interested in solid state batteries. And that seems to be one of the most promising ways. Sodium also has some safety advantages in terms of the way that it shorts, but solid state is probably the best answer.
Okay, shall we move on there and come back to questions at the end?
Okay. Sorry. Okay. So you probably know where this is going, given the topic of the webinar. We want single crystal diffraction, but we don't have large single crystals. So we turn to micro-ED as a way of getting 3D crystal structures with full 3D single crystal data from real battery grade samples. And to do this, we worked with Rigaku USA, who have a nice demonstration model of the Synergy ED. We're based in Houston and they're around, so they've been really great partners in this. And this is an instrument that is essentially a TEM that's optimized for diffraction, to take fast diffraction patterns with continuous rotation on any sort of TEM quality sample. So what we'll do is we'll take our typical battery sample here. In this case is sodium, nickel, a third, manganese, 2/3 O2, one of these layered metal O2 oxides. Crush it up really well, put it onto a TEM grid so that there's some parts of the particles. Here you can see a particle that we've crushed, put on the TEM grid, and you can see some parts are transmissive. You can kind of see through a portion of this crystallite, and that's enough to get a single crystal pattern from. As long as we have a little bit that's electron transmissive, we can get a diffraction pattern. And then the detector or the sample continuously rotates and collects lots of diffraction patterns to reconstruct as much of a reciprocal space as possible on that one tiny portion of one tiny crystallite of a real battery material. The metal oxide samples we're working with diffract very strongly because of the transition metals compared to something lighter that doesn't interact with electrons quite as much like an organic. So we get good resolution in just a few minutes. We tend to collect for about 5 minutes, or let's say 2 to 5 minutes. And we can get up down to 0.3 angstrom resolution. The data set's really quite beautiful on these samples. And from that, we're going to try to solve structures. And here's one of the structures we have solved that we'll talk about. So going back to our picture of a battery, you can think about all of the phases that are present in a battery. We are mostly focused on the positive electrode and how it changes, but there's interfaces. There's the solid state electrolyte, which we just talked about as a good solution to battery safety issues. There's the SEI and the lithium metal. There's all these phases, and you can start to think about what are the opportunities to start to get 3D crystal structures of some of these phases that you don't have available in bulk crystals. Oops. Okay. So just before we go into the practical examples, I'll just give a little note about working with the electron diffraction data. The advantages here really are that you can get single crystal diffraction on realistic battery materials. The collection times are very fast compared to X-ray crystallography, so just a few minutes. What that means in practice is that you can take a powder, sprinkle it onto a TEM grid, and go around in one session to multiple different particles and get a sense of the sort of diversity of phases that may be present. Sometimes we'll see little side products. We'll get a sense that we have some sodium carbonate there, or that there's multiple stacking sequences present in one battery sample. So you can get multiple structures. And then you can target with the TEM exactly where you want to go to get individual micro or nano phases that would be hard to isolate otherwise. There are some challenges as well. As you can see on the left here is a typical data set shown in reciprocal space in 3 dimensions. And what you can see is it looks like a wedge almost on top and bottom. That's because the TEM beam goes through the sample and the sample is able to be rotated, but it's often incomplete. It's often impossible to reconstruct a complete Ewald sphere. There's also issues of dynamical diffraction. Oh, and I'll say with our layered materials, the part of the Ewald sphere we're going to be missing is the part perpendicular to the electron beam. So that is the OOL direction of our single flat platelets, but that varies based on your crystal. We also have dynamical diffraction. So this is sort of the most famous issue, which is that electrons interact more strongly with atoms than X-rays do, and so as a effect, you can get double diffraction and other effects that can make it more difficult to solve structures. In practice, oftentimes the structures come out just fine, ignoring dynamical diffraction or handling it, but it's something that you have to think about. And then also the electron scattering factors are less straightforward than X-ray scattering factors. So there are ones that you can find tabulated in various sources and use, but there's some complexities, like the fact that they change quite a bit when you have an ion versus a neutral atom, and that matters in batteries. So we have to think about each of these things. We have really beautiful data sets, and we should be able to get great structures, but it's something we have to be aware of. All right, I will go through a couple examples, but first we have another question. Oh, I think you're muted.
Oops, sorry, I read all that out with the microphone off. Yeah, so I think everyone's got the idea anyway, and we can see that the home lab is winning, but there's quite a lot of synchrotron use, and a reasonable number have used micro-ED already. Not so many using neutrons. Okay, so I'll stop that there. Thank you very much, everyone. So back to you, Josh.
All right. Okay, so I'll end with two examples of the process that we would take to do this and some of the structures that we're looking at. The first will be an as synthesized battery material powder. So this is a powder material we made in the lab, actually with a known structure. So it's sort of a test case of how to do these measurements. And then the next was with a ex situ charged electrode. So this is a battery that we've charged part of the way. We know it's going through some phase transitions, but we want to know what the phase is. And so we'll disassemble it, take out the electrode, and then do micro-ED. All right. So for the first example, this is called P2 sodium cobalt oxide. P2 comes from the Delmas notation for layered oxides. It means that the sodium's in a prismatic environment and that there's two unique types of layers. That detail will come up later. For sample prep, we have one of these powders with varying size crystallites. We grind it up very well in a mortar and pestle first. And then we use 2 glass slides to grind a small amount even finer. This is an example. Our powders are not white. This is with a different powder. Ours would be dark, almost black. And then we take just a tiny amount of that very finely crushed powder, and we take the carbon grid and we kind of wipe it over to get some particles to stick to the grid. We use copper grids with lacy carbon between them, typically 3 millimeter grids, the standard TEM grids. Then when you load that into the diffractometer, you have a TEM view. So we find a particle that has an electron transparent portion. In this case, the particle is pretty big, but we were able to find a thin portion and collect a pattern that looks like this. And this is then indexed to find a likely unit cell. And so in this case, we found a hexagonal cell with A and B around 2.82 angstroms and C close to 11 angstroms. Just a note here, because of dynamical diffraction, oftentimes in the indexing procedure, you won't necessarily be able to definitively find a space group right away at this stage. The reason for this is twofold. One of them is that with dynamical diffraction, you can get intensity in positions that would otherwise be absent, systematic absences by the space group. So there's some ambiguity in the space group determination due to that. And then another reason is the incomplete Ewald sphere. Sometimes you don't have the part of Ewald sphere that would make unambiguous determination straightforward. So here we focus on getting a Laue group in a unit cell for the most part. And then in the structure solution step is where we'll evaluate space groups and hopefully come up with a sensible space group. And sometimes you can see systematic absences, but just something to be a little bit careful with. Okay, so we took this into a structure solution program. In this case, we used OLEX2, and we were using ShellXT to do the structure solution. And what we were able to find is that with that nice data set, which I think was about a 0.5 angstrom resolution, we were able to use the automated procedures to get a pretty good initial solution for the structure. What's shown here looks like this. If you were to expand this into a full unit cell, you would see that what it found is the 2 layers of cobalt oxide, COO2, which have octahedral coordination around the cobalt and edge sharing octahedra that form a continuous layer. And there's 2 of them in the unit cell. So one here and one here. This one's repeated. There's 2 in the unit cell, and they're stacked such that there's prismatic areas in between. So this has successfully found the P2 structure that we know we expect for sodium cobalt oxide, but it didn't know to put sodium into the site. That took a little bit extra work. We knew that there was sodium in there. And so in the refinement stage, we added some sodium into the prismatic sites and refined them. And we're able to get a final refined structure with an R value around just under 16% with the known space group from the literature, P63 over MMC. Just as a note, that R value would be really bad by X-ray crystallography standards. For electrons, with all these effects, we're not handling dynamical effects very carefully. We'll talk a little bit about that in the future. The R values around 10% would be excellent. 15% is actually pretty good with these samples. And then something that I like to do is we like to always check against powder diffraction, because when you're doing these measurements, you found one portion of one grain of your battery sample, and it's possible that that one structure that you found is not representative of the bulk. That may be quite interesting because in the real sample, there's some diversity, and with the TEM, you can pick out individual particles and solve individual structures. But if we're looking for the bulk structure, we'd like to take the model that we get from TEM or from micro-ED and at least verify that it matches the powder diffraction. So we have a sense that it is at least consistent with the bulk. As we said before, the powder diffraction may not be sufficient to solve all the details of the structure, but we can at least make sure that our micro-ED solution that we picked out of one particle is at least consistent with the bulk. Right, and in this case, we get a nice fit to lab XRD with this structure. All right, we have a little more, let's say, potentially realistic example is now to look at the sodium nickel manganese oxide battery cathode. This is a base chemistry that is in various modified forms. The base for a lot of the battery chemistries that are being commercialized right now are based on nickel manganese oxide, where nickel goes through redox from 2+ to 4+. And if you were to make this battery material, which has been well studied, you would see that there's a charge profile that has steps as you charge it. And each of those steps comes at specific special points. So 3/5 sodium, 1/2 sodium, 1/3 sodium, perhaps others. And so clearly there's some phase transitions that are happening, and we'd like to know the structures that happen as we charge. In practice, this is done in the lab with cells that look like this, coin cells or pouch cells. Sometimes we use, where we actually just buy the empty casings from CR2032 coin cells, like the ones that you would use in certain watches, and put inside are a stack of materials with a spring, spacer, an anode, which could be lithium or sodium metal, the electrolyte soaked into a glass fiber separator, and then a film of our cathode. And that film of the cathode is what we're studying. It's made out of the as-prepared battery material mixed with some carbon and polymer, PVDF, with solvent to make a slurry that you then can cast into a film. The carbon's there for conductivity, the polymer's there as a binder. So it's not just the material, it's sort of this hybrid film. Okay, and so we'd like to be able to study it. We can charge our battery up to a certain point, take a certain amount of sodium out of the cathode material, but we will then have to disassemble the cell by uncrimping it in a glove box, handling everything very rigorously air-free, scrape off that film. We then dissolve off a lot of the NMP that we dissolve a lot of the polymer binder with more NMP, centrifuge out, and recollect a little bit of powder that we can grind up. So this is can all be done in the glove box. When you do that, you then have a vial of powder, which in theory should be useful for TEM or for micro-ED. The way that we loaded it into the instrument is using the stage that's shown here, which is a cryo stage. There's also an air-free sample transfer stage, but it wasn't available to us at the time we were doing the measurement. So we used a standard cryo stage that allows for loading of cold samples. And the advantage of that is that this is all done under liquid nitrogen. So it's cold, but it's also an inert environment where you can work under liquid nitrogen. So in the glove box, we would prepare the TEM grids after this process of recollecting our partially cycled battery electrode into powder form, put it onto a TEM grid, and then seal it into a vial and take it to the instrument. At the instrument, you'd open the vial, which is under inert atmosphere, and immediately dump it into the liquid nitrogen. So now it's under liquid nitrogen. The TEM grids can then be loaded and worked with and manipulated entirely under liquid nitrogen, and this entire transfer can be put into the instrument with no air exposure or minimal air exposure. It does mean that the sample is going to be around 100 Kelvin or lower, so that could be an issue for some samples. Yeah, but this worked well for our sample. So we, for example, here I've looked at sodium nickel manganese oxide where it's partially desodiated and the X value is 0.5. It's mounted, you can see the particles here, and then we get a crystal structure, or a single crystal pattern that looks, again, quite nice, down to about 0.4, 0.5 resolution in this case. And in this case, solving with OLEX2 worked very well right off the bat. That needed sort of very little additional work. We got a structure that looks like this on the left. Of course, OLEX is mostly made for small molecules, and so when solid-state inorganic structures like this get plotted, it can look a little funny. It's drawing bonds that we wouldn't normally bond. So this may look quite strange, but it actually is the right structure. I'll show you that drawn a different way in a moment. And so found the structure and then did refinements here. And just a few notes on how these refinements actually work. The things to be aware of is when you can choose the structure factors. There's some baked into OLEX2. The UCLA ones are the ones we tend to use. But also, if you go to this website, there's a really nice database of the factors that you can find. And it includes not just the factors for neutral atoms, but also for ions. Ions interact very strongly. And so with electrons in different ways, whether they're positive or negative, and so it can change. And so I like to use the scattering factors for the ions rather than the neutral atoms. And you can find those here. And then one of these buttons, you can manually add them in. And then another point is that we are treating electron diffraction data as if it was kinematical, but really it has dynamical effects. It is possible to start to try to simulate those with other software, but when using standard refinements, we would typically just refine the extinction coefficient and it becomes absolutely massive. And that handles at least some portion of the dynamical effects well. So that's something that should always be refined, and we'll refine to large values to get a good fit. Okay. So here's the final structure that we came up with. The space group is PMN21, and the R value is 13.8%, which we were quite happy with. And what we see is that the sodium actually forms these sodium vacancy patterning that's like a zigzag with empty areas in between. So rather than being just partially occupied on every site, it forms a specific pattern that's zigzag. And that's associated with the superstructure. And we're able to have reasonably good confidence in that because we have the full, a pretty good completeness in our Ewald sphere. Once you have these structures, there's a lot that can now be done. This is now the basis for all sorts of simulations that can be done, but also even just looking at the structure. For example, this is a bond valence sum map, which shows a map of the areas in the structure that have the bond valence within 15% of 1. So in other words, the parts of the structures that would be happy to have a sodium sit in them. And this can be taken as an indication of if sodium is going to move through the structure, what's the pathway available to it? And so you can see that these sodium sites are connected by these nice pathways of areas that they can move through. And so we can analyze for example, sodium ion conduction pathways now that we have a structure. All right. And I used PyEbstantia, a nice free Python package to make these based on the CIF. All right. With that, I will I will leave you with these acknowledgments. Thank you very much to my group. Particularly, it was done by the measurements were done by these three on the right, Cindy, Kosavin, and Moynick. And we worked well with Rigaku USA, Pierre, Simon, Mark, Lee, and Jessica, among others, were extremely helpful in this project. So thank you very much.
Yeah, thank you. Hopefully this time I'm not still muted. Apologies for that little error earlier. So we do have quite a few questions to get through, and I think given the time, we're probably not going to get through them all. So we'll go until the hour, which is about 5 minutes from now, and anything we don't answer, we'll take up offline. Okay, so let's just start at the top. I also point out that you can upvote the questions if there's something there that you in the audience find more interesting for us to cover, given we have limited time. So the first question is, I understand that lithium-ion batteries are only expected to last something like 1,000 to 2,000 recharge cycles before significant degradation. How do sodium batteries compare in this regard? For example, do they have the potential to outlast lithium, or is this one of the challenges which is being faced?
This is one of the challenges that's being faced. So typically sodium will be a little less, but with the optimization and research that's gone in, the first sodium cathodes are also lasting thousands of cycles. Most likely we'll have to see the commercial cells have just been kind of made available in the last couple of weeks. And so a lot of that data is not available yet, but it seems it will be in that same region. I would say lithium is also, with lithium iron phosphate and the right anode chemistries, lithium is sneaking up even higher than a few thousand cycles.
Okay. What is the advantage of using the Synergy ED over just a normal TEM?
So the Synergy ED is, the way I see it, is it's essentially a TM that's just optimized to make it as easy as possible to take the diffraction patterns. Everything here could be done with a TM with the diffraction pattern. With a conventional system, you would have to take a a diffraction image, and then rotate the sample, take another, rotate another. And that process would probably, with sort of conventional hardware, take a few hours of TM time. It can then be reconstructed into an Ewald sphere, and you can do the structure solution. With the Synergy, everything's optimized. So you can just go to a particular particle and then see if you get a good sort of diffraction spots, and then allow it to rotate and collect the data continuously. So it's constantly rotating, has a fast detector. And so it just takes a few minutes. So we just get a lot done faster, essentially.
Yeah, and I would encourage whoever asked that question, if you haven't watched the earlier episode in this series, there's some discussion on this topic and in the introductory part. So the next question, someone you name dropped earlier has asked a question, James Steele. In your experience, is there an ideal size for the crystallites used in this technique, which I believe he's referring to micro-ED based on when the question came in? Do you expect, or have you observed any other negative effects from crushing the larger particles, or are these still completely representative of the uncrushed particles?
Yeah, very good questions, James. Typically, it's about 200 to 300 nanometers are the samples that we've gotten the best data on with these metal oxides. The reason we certainly are concerned that crushing could cause changes in some way, and that's one of the reasons why we then go to powder diffraction to try to verify that our models still make sense with powder diffraction. So it's definitely something to think about. But do note that oftentimes the particles we work with are actually much thicker, and we're just finding a small transparent portion of them rather than making a nano-sized powder, since that wouldn't be exactly representative of our battery samples.
Okay, so does the sample deteriorate under the electron beam when you have desodiated grains? And how much time do you have to use to get a pattern?
That's a good question. We haven't observed that. And I think that may also be an advantage of the continuous rotation. We're only measuring for about 2 to 5 minutes per sample rather than several hours.
Okay. I've heard of a technique called single photon diffraction from Dr. Brian Tobey last year. Is there any way to do this with ED? If so, is it possible to minimize the multiple scattering issue? So I guess you have to have heard of that technique to be able to answer that question, and I personally have not. So
I haven't either. Sorry.
okay. Next question. Do you have issues with dynamic range when indexing superstructures? Superlattice peaks, at least by X-ray, are often hundreds of thousands of times weaker than the main peaks.
Yeah, absolutely something that we think about. It's been pretty good. That's about all I can tell you. I can't quantify. We've often been able to see superstructure reflections. Let me see if I have a good example. So here in this pattern, you can see a sort of, well, at this angle, it looks not perfectly hexagonal, but it's a hexagonal sublattice. And then the superstructure peaks are these around here. You can see a smaller superstructure. They're very faint. The dynamic range seems sufficient for what we were looking at.
Okay, and I've just noticed that we have run out of time. So with that, I'll say thank you to Josh again for the excellent talk. It was very, very nice. Thank you. And a plug for the next episode in the series. So on Wednesday, the 6th of August, we'll be having a presentation on MOF research, so metal organic frameworks, from Professor Ross Forgan at the University of Glasgow. So I posted the link for the page to register for that earlier on, and I've just posted again some links to the product pages and other pages that might interest you. And with that, I guess we're finished. So thank you very much for joining us again, and we'll see you next time. Thank you again, Josh.